geometry students, and welcome to your geometry tutorial video. Today we're going to be covering lesson 7 of unit 10, and this is the very last lesson of this whole trimester. Hope you're all hanging in there and doing good. Let's get started with this and complete some geometry. Today we're going to be talking about special segments in circles. Special segments in circles. We already learned about all the special segments. We learned about tangents, we learned about secants, we learned about chords. There are a lot of special segments. Well, how do these segments relate to each other when they intersect? We have a few theorems that we're going to talk about and look at those theorems, and then we're going to use those theorems to solve some problems here. So let's get started with the first one. The first one has to do with the chords. It's called the segments of chord theorems, theorem 1015. It says if two chords intersect in a circle, so if I have two chords, here we have chord ED, if you'll notice there, we have chord AC. When they intersect in the circle here, notice they kind of break each other up into each chord being broken up into two parts. It says here's our theorem, here's the product, meaning if you multiply the lengths of the chord segments, they are equal to each other. So if I multiply the lengths of the two segments of the chords, then they are equal to each other. So for instance, AB plus times BC here, if I multiply these two together, that's going to be equal to the product of the other two segments of the other chord, ED, EB, and DB. Pretty awesome, huh? Well, let's look at it. Look at a few problems where we're going to solve for a different part of the segment of the chord using this theorem, 1015. Assume that the segments that appear to be tangents are tangents round to the nearest tenth if necessary, and we want to solve for x. So for this problem, we want to find this segment right there of that chord. And so I'm going to use this theorem 1015 to find that segment. I know that if I use segment theorem 1015, that 3 times 6, that the product of those two segments of that chord, 3 and 6, is equal to the product of the other two segments of the other chord, 2 times x here in this case. So we have 3 times 6 equals 2 times x. And that's an easy enough algebra problem for us to solve, because 3 times 6 gives me 18, and then we have 2 times x, which is 2x there. We'll divide by 2, and that means that x piece has to be 9 long. This segment is 9 units long. Pretty easy, huh? The products of the segments of the chords are equal to each other. That's all you're doing here. So if you're missing one, you can use this theorem to find that segment. So let's do one more again here. So again, we have the chord here. And so the products of the segments of these chords are equal to each other. So 8 and 8, if I multiply 8 and 8, that should be equal to 6 times x. 6 times x. Oh, I'm going to do this down here. So theorem 1015 again, that theorem we just dealt with. X times 6 is equal to 8 times 8. Multiply that out. You give me 6x here is equal to 8 times 8, which is 64. And then we want to divide by 6. Divide by 6, and you're going to get a fraction here. So let me get my calculator just to show you. We want to take 64 and divide by 6. And you're going to get 10.6666. If you want to write it a fraction, you can, but I think it said to round to the nearest tenth, so we'll say about 10.7. So we can say is about 10.7. Okay, easy enough, right? There's your first theorem. I believe we have maybe just one more or two more to deal with. And the next one is the secant theorem here, 1016. 1016, a secant theorem. So if I have two secants here intersecting on the exterior piece of a circle here, here's my example. Pretty similar to our last lesson here, but we're not dealing with the angles at all. Now we're dealing with the lengths of the segments. That's the difference from today's lesson and yesterday's lesson. Yesterday we're looking at the angles. Today I'm looking at the lengths of the segments. Okay? So they're saying if two secants intersect in the exterior of a circle, then the product of the measure of one secant segment and its external piece, external segment. So the product of the piece of the whole thing. Like for instance, all of AC times the external piece, and here's the external, I'm going to put EX for external, times this external piece is equal to the product of the measure of the other secant, its whole piece, times its external piece as well. So it's a little bit different here. Here we're saying that AC, this whole thing, AC times the exterior piece, AB, is equal to AE times its exterior piece, AD. If you want to, sometimes I write it down like this. We say the whole thing, the whole times the outside is equal to the whole, I'll write this, make sure I spell things right, times the outside. So the whole thing times the outside is equal to the whole thing times the outside. Maybe you can write it like that. And then we have one more, and this is the tangent secant theorem. Now the tangent secant theorem is a little bit different. This is theorem 1017. And a tangent secant theorem, this is tangent, you need a tangent and then you need a secant. A tangent and a secant. So you see here, JK is this tangent, and then JM is a secant. So if you have that, if you notice here your form here, if the tangent and secant intersect in the exterior part of a circle, then the square of the measure of the tangent, so we're going to square this. The tangent we're going to square. So the tangent we are going to square. And that is equal to the measure of the secant. Remember what we do with the secant? It is the whole piece, right? The whole secant. The product of the measure of the secant times its external piece. And here's the external piece. The whole thing times the external piece, the outside piece. So there's the form here that we're looking at with the tangent secant theorem. Tangent squared is equal to the whole secant times the exterior piece or outside piece. Alright, so those are the last two theorems here for this lesson. I know those are kind of weird, but if you have two secants, it's whole times outside equals whole times outside. If you have a tangent and a secant, then you square the tangent and then you do whole times outside for the secant. Let's look at a few problems here, and hopefully this will help us. So we're going to find x.